Gravitational potential energy 1. Write equations for change in gravitational potential energy near a planet's surface. Change in gravitational potential energy near a planet's surface. The mass of the object times g times the change in h. We have used that idea a lot in previous videos. What about the absolute gravitational potential energy in a two-mass system? We've met this one also already. We haven't really worked with it much. G, let's call it big M, little m, divided by r. Not r squared. Absolute gravitational potential energy in a two-mass system. If you have a planet and a moon, let's say, or a planet and a satellite, what's the gravitational potential energy between those two objects? That's how you do that. Let's show that Newton's law of gravity equation is, in fact, the negative derivative with respect to position of the gravitational potential energy equation. We said a long time ago that a conservative force is the negative derivative of the potential energy with respect to position. And I think previously we put a dx here, but in this case I'm going to put dr. It really doesn't matter. Let's try differentiating this equation right here. First of all, let me rewrite it to get that r out of the denominator. Negative big G, big M, little m, r to the minus 1. Now, when we take the derivative of this, we're going to differentiate with respect to r. So all of this other stuff, these are constants. So I'm going to say negative, and then we power down. So this negative 1 has to come out here, and we go r now to the minus 2. But we don't want the derivative of the potential energy. We want the negative derivative. So I got to put another negative in here. Burp. Negatives all over the place. Now, if you simplify that, two of these negatives end up canceling. And so what you get is you get an expression that looks like this. The opposite of G times M times other M divided by R squared. And that is Newton's law of gravity. Now, what's with the negative sign there? The negative sign indicates attraction. It indicates an attractive force, which gravity always is. And usually we omit it, don't we? Usually we omit that negative sign and we just go for the magnitude. And then based on the situation, we know which way it points. But there are some books that will show, hey, there's a negative sign right there. And that just means that the gravitational force is attractive. A couple more basics here. Anytime a mass moves against a gravitational field, it gains potential energy. When you lift a mass up, it gains potential energy. Anytime a mass moves with a gravitational field, that is, if you drop a mass, it's going to lose gravitational potential energy. Last thing, absolute gravitational potential energies are always negative. There's a negative sign in that equation. I'll write it one more time. U sub G is equal to negative G, one of the masses times the other mass divided by R. That is always going to be a negative number. Changes in gravitational potential energy could be positive, could be negative. Near the Earth, if we're raising something up, the gravitational potential energy, we can say, oh, it increases. And when it falls, it's going to decrease. It's going to be positive or it's going to be negative, depending on what we're doing with our masses. But absolute gravitational potential energies, always, always negative.